Hello everybody, my name is Claudia De Torre and I am a PhD student from University College London, and along with my colleague Andrea Mariani, also a PhD student from the Robotics Institute of Pisa, we are excited to present our review work on accelerating surgical robotics research, a review of 10 years with the dVRK, with all of you today. So without any further ado, let's just dive in. Why did we decide to review a very large number of publications about the dVRK? Well, because we thought it would have been a great occasion to celebrate 10 years anniversary of such a vibrant and in continuous growth community that has been working hard to generate high quality scientific publications. But also, on the other hand, we felt the need of helping avoiding confusions when newbies approach for the first time the system. Personally, I still remember the first time I Googled dVRK and I ended up on a situation that was very similar to this one, where I thought that the dVRK community was also producing music. Well, jokes aside, what we realized from a quick Google search of the string Vinci Research Kit, for example, is that the number of results is quite considerable. And then the first hit is directing towards the Intuitive Foundation website, which provides a general overview of the community and how to apply for the system. While in case of the search of the string dVRK, results appears to be smaller, and the first link directs towards the dVRK wiki page. The aforementioned resources are very useful for understanding the system and the motivation that brought to its creation. But what we had the feeling it was missing, it's a resource that could give a glimpse on what type of research can be carried out with such an extensive systems, and also generally summarize the number of publications that this community is generating. And as we can see from the graph, they are increasing exponentially. Now, let's have a look on how we managed to collect all these papers. So we started from the list of the user group, which is located on the Google group of the community. We then compared the outcome of this research with the timeline list from the dVRK wiki page. We generate a full list of community members. But specifically, we decided to group different labs belonging to the same institution under the same name, and not to consider industrial members that were not generating any scientific publications under their names, reducing therefore the total count of institutions. After the described filtering process, we obtain the final list of 36 academic institutions from everywhere in the world. After having defined all the actors involved, the next step is to start the search of all the publications. So specifically, we decided to proceed in a systematic way. We generated 3 different datasets from 3 different search protocols. We then screened them, removing outliers and combining them to generate a single database, avoiding duplicates. Starting from the first search protocol, we began looking at the PI URLs listed in the user group, and whenever the link was not correct or active, we were directing the search directly to the PI profile webpage and look for the dVRK publications, obtaining in this case a final number of 195 publications. As a second research protocol, we decided to use Google Scholar using the string Vinci Research Kit and filtering the results only between 2012 and 2021. This search produces 523 publications. As last database, we have used Dimension AI, which appeared to be a great tool for customized filtering criteria and that claims to have 30% more publication than comparable dataset currently available. We set up the same time interval and use the same string that we have used in Google Scholar. In this case, we obtain 394 papers. Once we collect all the papers, we then filter them following 2 different criteria. For one version of the paper, we maintain publications belonging to symposium, archive, and national conferences. while for the shortest one, we only consider peer-reviewed papers published in international journals or conferences. All the papers were manually checked in order to remove papers that were not published in English language or they were presenting the search string as a reference, although the reference paper were already excluded from the search. We finally obtained two different datasets. The longest version is the one currently published on arXiv, while the short one is currently conditionally accepted for a journal publication. From now on, all the following images and figure will be referring to the short journal version. For describing this huge body of publications, we identified 5 major research fields. Starting from the left, we have automation, followed by training, skill assessment, and gesture recognition, system simulation and modeling, followed by hardware implementation and integration, to end with imaging and vision. Naturally, we acknowledge that it's hard to determine a unique classification of the paper, as it is complex to define solid boundaries among research fields, which often feature high interconnection. However, we try to classify each publication according to the research field that better describe its final application. This histogram shows the dVRK community members for which at least one publication was found following our searching criteria. Also, all the publications are classified based on the aforementioned research fields. Just a little side note, in case of publication involving multiple centers, the publication was assigned to the principal investigator's affiliation. This is a figure that you can find in the review paper and wants to provide a visual indication on who is mainly working on what. I will now hand it over to Andrea, who will describe the application for each research field.
Thank you, Claudia. So let's analyze each research field to better explain the paper allocation and to identify the most popular applications inside each research field. The first field is automation. That means all the works automating any aspect of robotic surgery in order to improve the surgical workflow or to optimize the performances in a certain task. We decided to additionally group these research efforts based on the application of the proposed control strategy. So we first have general control that refers to works focused on developing new high-level control architectures without specializing on task-oriented applications. Then instrument control that groups all the contributions towards the automation of specific surgical subtasks like suturing, pick and place, or tissue manipulation, and so on. And finally, camera control that includes the literature that investigated how to relieve the surgeon from switching between the tool and the endoscopic camera control by introducing autonomous navigation of the endoscope itself. Robotics, with the additional encoder information compared to normal instrumentation, especially in an open platform such as the dVRK, open attractive opportunities to study gestures, to assess technical skills, or to improve learning. So a second remarkable research field that we identified is called training, skill assessment, and gesture recognition. In this field, we grouped all the publications where new training platforms and protocols were designed and evaluated, as well as the research efforts towards learning enhancement by multisensory training augmentation. Here, a special mention goes to haptic guidance or virtual fixtures. That means the application of forces to the trainees' manipulators to guide and teach the correct motion. As a fundamental component of learning, skill assessment has received attention, especially towards objective and automated technical skill evaluation. Finally, workflow analysis by surgical gesture identification and segmentation was widely investigated with particular interest in combining image analysis and robot kinematics. The next research field is called hardware implementation and integration. It is quite a heterogeneous category, thus featuring the highest number of publications. First of all, here we find all the papers published during the development of the dVRK platform itself. Then we have works related to haptics, trying to integrate the surgical tools with force sensing or using virtual fixtures as intraoperative guidance tool, as well as taking advantage of augmented reality and visual overlays to provide the surgeon with visual feedback about forces, the so-called pseudo-haptics. Some works focused on the design and integration of new surgical tools, like instruments and sensing tools, while others reported the development of new control interfaces, like using head-mounted displays to control the camera or improving the ergonomics and the portability of the master console. To optimize the surgical workflow, some research efforts try to enhance the surgeon's awareness and perception or to improve the teleoperation capabilities of the Da Vinci system. Finally, few additional works investigated the use of the dVRK beyond its current surgical intent, both in other surgical specialties like retinal surgery or for non-surgical applications like using the master controllers to drive vehicles in simulation. After the largest field, we move to the smallest one, system simulation and modeling. We notice that the small size of this field is partially due to our classification criteria, since many papers using simulation have been already classified in other fields. This field contains only studies that focus on the integration of the dVRK into simulation environments without any direct application inside the publication itself. We identified few works focused on optimizing simulation to obtain realistic robot interactions with rigid and soft objects, as well as works related to robot parameterization, that means the identification of the kinematics and dynamics properties of the robotic arms, like for external force estimation or other applications. As essential building blocks of computer-assisted interventions, we can miss imaging and vision. This field encompasses all the publications related to the processing of the images acquired by the endoscopic camera of the Da Vinci. Here we find camera and eye calibration that includes publications investigating approaches to register the coordinate systems of the endoscope and the surgical tools, as well as determining the camera intrinsic parameters. A wide range of papers reported algorithms aimed at detecting, segmenting, and tracking important elements in the surgical scene, such as surgical instruments or tissue features, and so on. Image processing was also finalized to special mapping and understanding, like to estimate the depth of the workspace or to automatically remove smoke from the surgeon's field of view. And finally, the dVRK research tried to keep up with novel imaging capabilities like interfacing standard imaging with the one from miniaturized ultrasound probes or photoacoustic imaging, or also implementing other kinds of image augmentation to assist the surgeon throughout the surgical procedure. In the initial pool of publications originated by our search protocol, there were also some reviews that cite the dVRK. These include comprehensive reviews on the state-of-the-art of robotic surgery and its future research directions, as well as works that reviewed the legal implications of using artificial intelligence and general aspects of autonomy in robotic surgery, or other reviews that focus on human aspects in robotic interaction, as well as the use of virtual and augmented reality in robotic surgery. The dVRK, as an open platform, allows to read and write all the data flowing in the system. So, in parallel with the research field analysis that we have just seen, we provided a second clustering criterion to classify the dVRK-related publications based on the data that they used. We then defined few data classes based on the data used or collected to underpin each publication. The 5 different data types are the ones in the figures. So moving from the left, raw images, kinematics data, dynamics data, system data that are the data associated to the robot teleoperation states, and finally, external data. That means all the data associated with additional technologies that were connected and integrated with the dVRK platform in the experimental setup. In the review paper, you can find this sum-up table that, for each research field, for each data type, and for each research group, reports the corresponding publication. To summarize the data type analysis, this histogram shows the percentage of usage of each data type across each research field. Again, we can notice the importance of images in robotic surgery, since in almost all the categories, images crosses the 50% of usage. The extensive use of kinematics and dynamics data also highlights the importance of having a research platform as the dVRK that facilitates the ability to take advantage of robots as haptic interfaces and to make use of the system's data generation capabilities. So we got close to the conclusion of this presentation. In this work, we tried to summarize the research outcomes related to the first decade with the dVRK. We collected more than 250 publications that are exponentially increasing year by year. We pointed out how these publications rely on a massive usage of data that was facilitated by the dVRK platform. This can be an interesting stimulus for reflecting on the acceleration of surgical robotic research and how to design open and compliant research platforms to boost the transition of research efforts into clinically meaningful solutions. We hope this work can also offer to the dVRK adapters a comprehensive overview of the ongoing research and a synopsis of the activities from the dVRK community members across the globe. You will find shortly a dedicated page with all the dVRK community publications that we collected, and we really hope that we as a community can keep this page updated in the following. The publications at this webpage will be marked with custom labels related to their research field and the data types that they use. To really conclude and to fuel later discussion, we may wonder which community wishes arise after all this dVRK literature review. Probably driven by our background, mainly focused on automation and training, Claudia and I would like to stress the following. First of all, there are a lot of amazing works involving user studies, and it would be extremely helpful to have a centralized and standardized storage of this data so that the community could later take advantage of them to develop, train, and test algorithms. Secondly, during the recent years, several simulation environments were developed to specifically address training or automation research. Instead, it would be great to have a joint effort from the community towards the development of a single, fully enabled simulation environment. This was the very end of our presentation. We thank all of you for listening, but also for contributing to all the dVRK works we have just reviewed during the presentation. Thank you.